In this session, we'd like to solve the Schrödinger equation in the potential wells. So in the particle in the box, potential becomes infinities at the x equals 0 and x equals L. But in the case of the potential well, height of the potential becomes finite. So particle exists in the square potential well. So these situations correspond to electron inside of the metal. Then Schrödinger equation is expressed this one's energy is lower than the potential energy. So if you draw the energy, this is height becomes, this is energy levels. So this is U sub 0, height of the potential. This is x coordinate, 0, and the box has a width of the L. The energy of the particle is this quantity E. Energy is given by the E. E is smaller than the U sub 0. So the particle is expected is bounded inside of the box. Most of the time, Schrödinger equations is expressed this equation inside of the box because the U equals 0. And the outside of the box Schrödinger equation is this one. So big difference between these two equations. The proportional constant of the psi becomes negative. This is lower than 0. So in the case of the outside of the box, this becomes positive. So solution becomes different. In the case of the psi inside of a box, like a particle in a box case, using the cosine and sine functions, we can express the solutions. So I don't repeat the same calculations because I have already explained how to get these solutions. In the case of the outside the box, this becomes a positive. This becomes just an exponential function. Exponential kappa x or exponential minus kappa x. And so this part it becomes a kappa squares. If you write down the solution of the psi, you expressed c exponential kappa x plus d when the x is larger than L. But in this situation, we should consider x is equal to the infinities. Then the kappa is a positive quantities, so this terms is equal to the infinity. So probability equal to the infinities when the x is equal to the infinities. So this is not true, so we have to think the c have to be 0. So we remove the this term. Same reason for the in this situation the x is equal to the minus infinities. D exponential minus kappa x is equal to the infinity. So we'd like to remove this quantities. So the psi can be expressed just only c kappa x when the x is less than the 0, or d exponential minus kappa x when the x is larger than the L. Between the 0 to the L, you can express a cosine kx plus b sine kx. Then we apply the boundary conditions. Psi x derivative of the psi is a continuous at x equals 0 and x equals L. So these two have to be the constant value, same values. Then I can show you. Solutions can be expressed. Psi is a c exponential kappa x at x equal less than 0. 0 x L. This is a cosine kx plus b sine kx. And the x is larger than the L. This becomes d exponential minus kappa x. So we have these equations. For the derivatives, you can easily calculate. It becomes c kappa exponential kappa x. This is minus a k sine kx plus bk cosine kx. This is minus d kappa exponential minus kappa x. So we have this equation. We are going to use these equations. So for the boundary condition for the C0. So you can use equations for this and this equation. You can use this equation. You substitute x equals 0. So from this equation, you can easily find c equal a. Also, you can find the c dash 0. So in these situations, you can compare these two. So c kappa equal bk. So from these equations, you can find b is expressed as c, but c as actually this is equal to the a. So b is expressed kappa over ka. Okay, so we have said that this is the equation 1, this is the equation 2. So b and c is expressed with a, capital A. Okay. And then another equation for the c dash l. So from these conditions, you can compare with these equations. So from these equations, you can find d equal a exponential kappa l k over kappa sine kl minus cosine kl. So this is the equation 3. So you can express c, b, d with the a. Okay. Then you can substitute these equations back to the original equation. Then we can express the wave functions. X equals less than 0, a exponential kappa x 0x l. This becomes a cosine kx plus kappa over k sine kx, and the x is larger than the capital L. This becomes a k over kappa sine kl minus cosine kl exponential minus kappa x minus l. So we have these solutions. Look at these equations carefully. So first of all, we'd like to change this cosine kx is expressed cosine k x minus L over 2. L over 2 is the middle point in the potential box plus KL over 2. So this means use the addition formula for the trigonometric functions. Cosine kx minus L over 2. cosine KL over 2 minus sine kx minus L over 2 sine KL over 2. For the sines, sine kx minus L over 2 plus KL over 2. So addition formula for the sine. Sine kx minus L over 2 cosine KL over 2 plus cosine kx minus L over 2 sine KL over 2. So you can express the equations here. Then you can substitute cosine and sine into the original equations. Then it becomes cosine kx plus kappa over k sine kx is expressed cosine k x minus L over 2 cosine KL over 2 plus kappa over k sine KL over 2 plus sine k x minus L over 2 kappa over k cosine KL over 2 minus sine KL over 2. So you can express these functions. First terms is a cosine. This is even functions with respect to the x equal L over 2, even functions. And the sine functions, this is odd functions. So functions can be expressed the sum of the even function and the odd functions. All the function can be expressed with the sum of the even function and the odd functions. I just show you that. Psi in the inside of the box can be expressed the sum of the even function and odd functions. So we have already used the boundary condition psi0, psi dash 0, psi dash L. We don't use a psi L. So we'd like to use a boundary condition for the psi L. Psi L. This is the expressed cosine KL plus kappa over k sine KL equal k over kappa sine KL minus cosine KL. So we compare these two terms, this and this terms. If you substitute x equal, you can just compare the inside of these parentheses. If you substitute x equal L. Okay. So this is the equations. I write them. Then we'd like to change these equations a little bit. This equation becomes 2 cosine KL equal k over kappa minus kappa over k sine KL. Then we can apply the addition formula, double angle formulas. 2. This is cosine square KL over 2 minus sine squares KL over 2 equal K over kappa minus kappa over K. So this is 2 sine KL over 2 cosine KL over 2. So 2 appears in the both sides, so it's going to be cancelled out. So this equation, we have a four terms because of these terms. It's going to be, this equation can be expressed. Cosine KL over 2 plus kappa over K sine KL over 2 times cosine KL over 2 minus K over kappa sine KL over 2 equals 0. Then we have two choices. This is equal to 0 or this is equal to 0. So this means cosine KL over 2 plus kappa over K sine KL over 2 equals 0. Or cosine KL over 2 minus K over kappa sine KL over 2 equals 0. So you have two choices. This or this. In the blue case, you can return to the blue case. This part is going to be 0. So it becomes auto function. So these situations, Cx becomes A kappa over K cosine KL over 2 minus sine KL over 2 sine K x minus L over 2. Okay, so we have two situations. So, but in these situations, x 0, x L. So this is auto functions. If you draw the x L over 2, so it should be that these kind of the auto functions we have. So wave functions becomes auto. In the case of the green situations, Cx, this is going to be 0. So this is A cosine KL over 2 plus kappa over K sine KL over 2 times cosine K x minus L over 2. So this is the even functions. This is x is between the 0 to the L. So in these situations, L over 2 are even functions. Okay, we have this situation. Then we'd like to solve the each case, blue case and the green case. for the blue case, you can express cosine KL over 2 plus kappa over K sine KL over 2 equals 0. So this means tangent KL over 2 equal minus K over kappa. So this is minus KL over kappa L. So by the way, we'd like to remember the expression of the K squares is 2me over h bar squares. And the kappa squares equal to m u sub 0 minus e over h bar squares. So kappa and k is related. So if you introduce a new variable z is a kl, then kappa squares L squares is expressed 2m u sub 0 over h bar squares L squares minus 2m e over h bar squares L squares. If you introduce a new variable, the g sub 0, so this is, if you substitute, this is g sub 0 square minus g square. This is correspond to g square because this is g squares equal k square L squares. This corresponds to g squares. So kappa square L squares is g squares. So substitute, this is g sub 0 squares. So kappa L equals squared g sub 0 square minus g square. You can consider. Then if you substitute instead of the k and the kappa, if you use g, it becomes tangent g over 2 equal minus g over squared g sub 0 square minus g square. Okay, so we have this case is a blue case. Blue case. So when you consider blue case, this is the auto function. So the solutions becomes auto. Also, we have another situation for the green case. Green case is a cosine KL over 2 minus K over kappa sine KL over 2 equals 0. So using the similar equations, you can find tangent z over 2 equal square root g sub 0 square minus g square over g. So this is case of the even functions. So we have a two case. Then the solution of the g should be the intersection between the tangent functions and the right hand side. Then we'd like to draw the curve. Then g have to be the positive quantities. Z 0. So take a pi. So this is tangent functions. Tangent z over 2. And this is pi. And 2 pi. 3 pi. So tangent is expressed This is tangent functions. Then we'd like to draw these functions. We'd like to draw g sub 0. You have to choose g sub 0 is between these 2 points. You can consider, for example, g sub 0 is in this situation I choose a 2.3 pi. You can choose any values. So in these situations, you can draw the blue curves. Blue ones is expressed these curves. This is minus g over square root g sub 0 square minus g squares. Okay, so this cannot cross this line. The intersections between the two curves give us the solution, one of the solutions. And also we have a case of the green curves. So green case is here. In this situation, if you substitute g equals g sub 0, it becomes 0. So it becomes starting from this point. And it goes to the infinity. This is a square root. G sub 0 squares minus g squares over g. So in these situations, we have two solutions, here and here. So actually the solutions, we have only the three solutions because there are three intersections. So these two cases, it's even functions. In the blue case, this is odd functions. The g sub 1, this point, you can use a graphic softwares or some computer softwares to find that these values is 4.82. And for the green case, this is 2.45. This point is expressed 6.89. Is 7.23. So in this situation, only the three bound state exist. Energy is expressed h bar squares over 2ml squares and the g squares. So you can substitute g sub 1, g sub 2, g sub 3. If you draw the vertical line, is the energy divided by h bar squares 2ml squares d squares energy state. So this is 0. And then this is the height of the g sub 0 square. This is 52.2, correspond to the height of the potentials. The energy, lowest energy, is given by the actually the even functions. This even functions. So green curves. So lowest energy is given by the green curves. This is g sub 1. Is a 6.00. This is lowest energy, even function. And the third is also g sub 3 square, 47.5. So two bound states exist for the even function. For the odd functions, second state, so first excited state is actually odd functions. It's 23.2. By solving the Schrödinger equations, we discovered three bound states. The wave functions. for the first wave functions is expressed 0 and L. Looks like these wave functions you have. So even outside of the box, it cannot become 0. So this is even function with respect to the L of x equal L over 2. This is the ground state. The next state is 0, L. So this situation is just antisymmetric. This is the wave functions for the first excited state. And last one is x 0 L over 2. This is highest energy bound state. So we have these 3 states, 1, 2, 3 states. Okay, so today's sessions may be a little bit difficult to follow. Okay, this is the end of this session.